Okay, welcome to the afternoon session. Our first speaker today is Matteo Casati from Ningbo University, who will tell us about multi-component Hamiltonian difference operators.
Okay. As everyone, I would like to start thanking the organizer for the kindly invitation and warm hospitality. This place is always amazing, and the conference is extremely interesting, to the point that I almost feel the need to apologize, because it will look like I make everyone dumber with my talk compared with the talks that we had in the last couple of days. However, this story is about the structure of differential difference Hamiltonian systems, or as some people call them, semi-discrete system. And this is a story about the investigation of the possible Hamiltonian structure that can be used to define or to generate these systems. So by semi-discrete or differential difference system, we mean systems of evolutionary type for a continuous time on a lattice. And now here I do one-dimensional lattice because first, most of the examples that are studied are of this type. Second, there are results here and much less in more general. And third, it is simpler. And of course, we can think of it as a dynamic on the lattice. The notation that many people use for that is the time evolution of some function u in these different sites. So uk as k labeled by the site by the site size, but being a translation and invariant mean that the dynamics in each site is the same as the dynamic in another site. I mean, is regulated by the same equation, and so this system can be packed in a single differential difference equation for a function on discrete space and continuous time, where we introduce and we use the shift operator to evaluate the function in different position. So the shift applied to a function to the function, it's very simple. Simply evaluates the function farther up or farther down if you use the inverse. And the simplest example of integrable equation of this type is the Volterra lattice. Again, I don't want to make everything dumb, but it's like a multi-species generalization of Lotka-Volterra system about predator and prey. And this system, which can be written in this way for each lattice site, for each species k, can be written in this differential difference form in this way. And it is, as it is well known, integrable according to pretty much every definition of integrability you may like. If you like to say that a system is integrable because you find the Lax representation, then of course it is Lax integrable, but it is also Liouville integrable, namely it admits an infinite sequence of commuting, on conserved quantities in involutions, and each of them correspond to some symmetries that are commuting. And finally, what it is more important on my viewpoint, I mean, not in my viewpoint, what I study normally is this is integrable also because you can assess that it's integrable because it admits a bi-Hamiltonian formulation. And the first question, very simple, is what do we mean by bi-Hamiltonian structure for an equation of this type? Now, why does it got stuck? Okay, and the way to describe, so this is the question of describing what it is called the Hamiltonian differential difference equation, and this story, at least of the story of the formalization of this theory, dates back to a paper or a report by Cooper-Schmidt, where he adapted the formal variational calculus that was already used for several, maybe 10 years, to study integrable PDEs, to the differential difference case. And also in that paper, there are some even further generalization of considering both spatial, continuous, and discrete system. The idea is that first we need to understand what's going on for our system, our equations, our function U's, and be element in some algebra, an algebra that's called the algebra of difference function. The number of components of the system, or if you like, the way this equation here is, this is a scalar equation, an equation for only a function U. But if you have a multi-component equation, you have L variables or L generators of your algebra, and a local functional or an observable, if you like the physicist language, over this algebra is an element of this quotient space difference function modulo the action of shift -1. This is a formal way of seeing the integration or the sum over all the lattice sides of a density. Probably most of the people are more familiar with the differential case. In the differential case, we have that the space of local functionals is formally considered as the quotient of the algebra of differential polynomials modulo total derivatives. This is the discrete version of that picture, meaning that the integral, or the sum over all the satisfied of a function of A, is the same as the sum over all the sides of a shifted function of A.
The right-hand side is a summation?
I haven't arrived to the question. Yeah, this is summation over J if the system is multi-component. Having the fact that the system is evolutionary means that the PDE here, or the time derivative of function U, should commute with the shift operator, and this can be described by introducing what are called evolutionary vector fields, so the derivations of the algebra A commuting with shift, and we say that the system is Hamiltonian if this evolutionary vector field can be written by the action of some difference operator on the variational derivatives of a local functional. What is exactly the variational derivative here? It's a different formula than the standard Euler operator that we normally use for PDEs, but it has the same property, namely the variational derivative of an element in the kernel of the projection from A to F is 0, unless this element, is a constant. Better. If it is a constant, is in the kernel and it is 0, too, so that's perfectly fine. And this Pij is, an operator that has some properties, because we want that define its being Hamiltonian, and the properties that the operator P must have are such that, as usual, you can define a Lie algebra between local functionals by the action of the vector field xg on F, and then the functor or the mapping between a Hamiltonian vector field, between a local functional and the corresponding evolutionary derivation is a Lie algebra action satisfying the standard, I would say, classical mechanics relation between commutator of vector fields and Poisson brackets. Notice, it's not extremely relevant in this area, in this studying Hamiltonian, I would say abelian normal differential difference equation, but notice that instead of giving a property directly on P, I prefer to define a Hamiltonian operator or Hamiltonian structure by these two requirements, because different category will give you different, well, a different notion of skew adjointness of P, different notion of what means that there is a bivector, which is a Poisson bivector, but what we are interested in the end of the day are these two properties. So if you like, this is an operational definition of a Hamiltonian operator, of a Hamiltonian structure. For example, as I mentioned before, the Volterra lattice is not just Hamiltonian, but bi-Hamiltonian, meaning it can be written as an Hamiltonian vector field for two different Hamiltonian structures and two different corresponding Hamiltonian local functionals, and the two Hamiltonian structures, the two Hamiltonian operators, are compatible. As a standard definition, any linear combination is Hamiltonian. This is one case. Now what I would like to do is describe in general how we can characterize these operators, and try to mention some results, some study that we did first with Jinping Wang and then with Daniele Valeri about the classification problem for these structures. Because despite being a very old subject, there are, best of our knowledge, not much general results on the structure of these operators. Now, the first point is, how can we formalize difference operator in a way that they define Hamiltonian structures? And in the last 50 years, there have been showed different approaches in general, I would say, to the theory of Hamiltonian operators. But surely the oldest is deciding to focus on the properties of the operator. Let's say that the Hamiltonian structure is some differential of difference operator with some linear and some nonlinear constraint on it. This is absolutely fine. This is different, though. If you ever, I mean, in a sense, every time you do this study, you must rediscover this property, because it's different, the properties, if they are differential, if they are difference, if they are acting on some commutative space or on some non-commutative space, etc. A more abstract characterization of this operator on algebraic terms, it has been done by essentially the school of De Sole and Katz, because first Barakat, De Sole, and Katz in 2009 introduced the notion of Poisson vertex algebras, that is an algebraic formulation of Hamiltonian operators for PDEs. This can be and has been generalized for a higher dimensional space, namely space with more than one in the space dimension. This has been, that's our case, extended to the so-called multiplicative case that describes Hamiltonian difference operator. These are a couple of papers by De Sole, Katz, Valeri, and Wakimoto, not so old. And then, since already the work of Olver, so work of Olver, I mean really the book of Olver, so in early 90s, there is the idea that you can characterize Hamiltonian structures in terms of some kind of functional, I would say, Poisson geometry, namely describing evolutionary system and corresponding Hamiltonian structures in terms of vector field and bivector fields with some Scout and torsion vanishing that characterize Poisson operators, etc. And these, well, somehow originally is present in other work, but has been studied and used very deeply later by, well, in different cases, mostly for PDEs, but I must say, but still, by Dubrovin and Zhang, several recent and less recent papers by Siqi Liu and Eugene Zhang. And in the difference case is something that we adapted together with Jinping Wang several years ago to study the Poisson cohomology, or as you will see later, the classification problem of this structure. And I would say the nickname for this functional approach is theta formalism, because we study multi-vector fields in general as elements on a supermanifold, as I will discuss later. Because the idea of this geometrical approach to Hamiltonian operators, the Hamiltonian structure, is, I would say, in a sense, very simple. We know from no, well, not from ever, but at least from the early 20th century, that Hamiltonian systems can be read with geometrical glasses, with geometrical eyes, namely using the language of first symplectic and then of Poisson geometry. And I think that this is convenient and useful also not only for standard classical finite dimensional system, but also for these evolutionary PDEs and differential difference equation. The plan is the following. First, I will make, probably it's not really needed with this audience, it's more needed with audience in integrable system traditionally, make a little bit of the case of description of this system in geometrical way, and then I will describe, as we can use this Poisson geometry language to define all the structure of an integrable system of differential difference equation. The first thing to say is that, well, apparently, our system of differential difference equations are just that, are equations for functions. But this is not really the case, meaning in integrable system, in geometry, we always do a lot of transformation of our equations. And the way that the equation transform and the way our object transform under change of coordinates, let them be point transformation, namely just transformation of coordinates on the manifold where these functions can be seen as coordinate, or even more advanced, more complicated Murat transformation involving higher jets on higher shifts of the function. All these transformations affect the expressions that we write in a way that is not the way in which functions transform under change of coordinates. This is, if you have done it concretely, it's very obvious. If you take an equation, an evolutionary equation, you will see that the right-hand side transforms as component of a vector field, not as a function. If you take a conserved quantity and you perform a change of coordinates, you will see that the variational derivative of your conserved quantity transforms as a one-form, not as a function. And again, in particular, if you take your Hamiltonian operator and change the coordinates, it transforms as a 2-0 tensor under change of coordinates, namely under transformation involving these functions u that you use to write your system. And even if you do something more advanced than just changing, but then just making so-called point transformation, but you involve also higher shifts or higher derivatives of your function u, these transform as Frechet derivatives at the adjoint of the Frechet derivative of this transformation. Again, clarifying or making it quite apparent that these objects are not simply bunch of elements of your space of differential polynomials over difference functions, but geometrical objects. And so that makes sense to study them in geometrical way. Now, how do we study these functional vector fields and functional bivectors, as the Hamiltonian structure is in geometrical terms? One of the ideas that it's useful because makes all the formula in all the different cases the same is remembering or discovering that it is rather well known the fact that if you take any differentiable manifold and construct the cotangent bundle of this manifold and reverse the parity of the fibers, or if you like it better, increase the degree of the fiber by 1, you obtain a supermanifold that is isomorphic to the complex of polyvector fields on the original manifold. That's a finite dimensional differential geometry result. Not only that, since your cotangent bundle is canonically a symplectic manifold, even this supermanifold has a canonical symplectic structure. And this symplectic structure is exactly, under this isomorphism, the Schouten bracket of polyvector fields on the original manifold. The Schouten bracket of polyvector fields is the generalization of the Lie bracket of the commutator of vector fields to all the exterior algebra of vector fields over the manifold. It has some, I would say, odd, not in the sense of strange, but in the sense of degree -1 grading for skew symmetry and Jacobi identity. The concrete construction of this is that when you study your generators on A, on the difference function, you have the generators of A, you introduce all the shift variables, un. Here now, u1 means the function after one shift, u2 after two shifts, etc. And each of these coordinates, you get its twin, its so-called, I mean, the idea is that it's conjugate momentum, but this conjugate momentum is a Grassmann number, so they are anti-commuting variables. Your supermanifold, when you have commuting and anti-commuting manifold, is a space of polynomial function in the odd variables, and the degree with respect of these odd variable theta correspond to 0 vectors, 1 vectors, 2 vectors, etc. over the original manifold. So we extend the densities of local functional or the differential difference function to polynomials in theta with coefficient in A, and again we define the corresponding integral of these objects. Statement, this Fx space is isomorphic to the complex of local polyvector fields on the manifold. What is functional polyvector fields? A p-alternating map from F to F, that because of this being defined on F and is alternating, shows an identification between local p-vector fields and p-1 skew adjoint difference operators. So, for example, our bivectors that we look Hamiltonian or Poisson structures in are difference operators, or are defined by difference operator by this formula, and the isomorphism between complex of polyvector fields and this space of this element of the supermanifold is very, very somehow straightforward. Each of these thetas that, if acted on with the shift, becomes theta to 1, theta to 2, etc., is somehow the eigenpost of the variational derivative of the functional which will enter in the action of the polyvector field. The canonical symplectic structure on this space F becomes this Schouten bracket, and explicitly as this formula. With this, I mean, exactly with this choice of position of derivative with respect of u and of theta, you get exactly the same grading as a Gerstenhaber algebra should have, which is defining property of a Schouten bracket. In the literature, you might find the expression, similar expression with some slightly different sign. This is confusing because they call Schouten brackets that are not satisfy the right grading. It is really not that important because the relevant result is always up to the sign, namely, we say that a bivector corresponds to a Hamiltonian operator, and in fact, the bivector will fit our definition of Hamiltonian operator if its Schouten bracket with itself is 0. So apart from all the machinery you use to construct it, this is the same as classical mechanics. And this as the same as in classical mechanics, now you have Schouten bracket and Poisson bivector, you have everything. Because you can define the Poisson bracket just by the action of the Hamiltonian vector field on the functional. The Hamiltonian vector field is the action of the bivector on the functional, and then by essentially what are general properties of Poisson of Schouten bracket, you have all the all the properties that you ask for a Hamiltonian structure defined in this way. This is very simple. However, what is not as simple is trying to see that in practice for difference operators. We do some simpler assumption, namely we decide to study local difference operators. By local means that they are polynomial in the shift operator. And so, for example, objects that you may find like shift minus 1 inverse, these are not allowed in our definition of local operator. In general, a local operator can be written in this way. Here there are sum over L, which when written in this way is not very clear. And in this way, well, we define what is the order of the operator is the pair of integers in which through which the powers of the shift range. And the skew adjoint operator, skew adjoint with respect with the integral we defined, must have this property. And in particular, it's very simple to show that a local bivector is in one-to-one correspondent with this skew adjoint difference operator. That's the easy part, is a linear requirement, a linear condition. The problem of the classification, there are actually two problems. The first problem is finding all the operators that up to change of variable give you a Poisson bivector. And the second part of the problem is what happens to your operator if you change coordinate. Well, if you have some generalized change of coordinates, namely a Neural transformation. Let's say that we have, since we study integrable system and we are interested in bi-Hamiltonian system, let's say that we have two compatible bivectors. So P is Poisson, and P and Q are compatible, namely the Schotten bracket vanishes. In this way, we can call, or we can say that Q is an infinitesimal deformation of P, infinitesimal deformation, because any linear combination of P with Q satisfies Jacobi identity, or satisfies vanishing of the Schotten torsion, more precisely, up to the order epsilon. If this deformation is Hamiltonian, namely P and Q form a bi-Hamiltonian pair, that will translate in Q and Q equals 0. Notice that if Q, that is an infinitesimal deformation of P, is obtained by the Lie derivative of P along some vector field X, we say that the deformation is trivial. Or someone would say that Q is P exact. The problem of the classification of the pairs now is finding non-trivial compatible deformations of the first operator, because when you have the first, you have a Poisson bivector, you have a Hamiltonian operator, you can immediately, by action of any vector field, find an infinitesimal deformation. And then, under some condition that I will not discuss deeply in this talk, you can take an infinitesimal deformation and extend it to higher order and higher order to obtain finally a Hamiltonian operator, or simpler, as I will do here, if we take an infinitesimal operator, an infinitesimal deformation which is already a deformation, namely it is already Hamiltonian by itself, you can see that non-equivalent ones, namely non-trivial operators, are inequivalent up to Neural transformation. So you have different families of bi-Hamiltonian pairs. How to do this? The way, or how to see this problem? The way of seeing this problem is using a standard object in Poisson geometry, that is the Poisson-Lie-Knirowitz complex of your space of local polyvector fields and the corresponding cohomology. This because elements on the second cohomology group are non-trivial infinitesimal deformations, and I will not discuss here, but elements of the third cohomology group will be obstruction to go from the infinitesimal to the finite deformation. Explicitly, let's assume that the second cohomology of your Poisson by vector is trivial. This means that when you have a compatible Hamiltonian operator, this Hamiltonian is x exact. This operator is x exact. Here is p exact. And that means that if you take the exponential map of this adjoint action of x over p, or of the lead derivative of p over x, and apply it to p, you get at first order your second element of the bi-Hamiltonian pair, and in principle a longer tail. But you can explicitly check, and you will say that this second element of the tail is again p exact. And being p exact, it means that it's written and can be written as the action on p of another vector field, and you extend this vector field to make your transformation from p and q finite, essentially, in closed form. So compatible bi-Hamiltonian structure plus trivial Poisson cohomology gives you all these bi-Hamiltonian pairs are equivalent under Muir transformation. And you would like to take the bi-Hamiltonian pairs and classify modulo this Muir transformation, because after all, you can regard Muir transformation as the natural set of transformation on the space A. So classification result, then, it's two different parts. First is the problem of the classification of the Hamiltonian operator of the single P up to coordinate change on the target manifold, so up to point transformation, I would say. Second, the problem of classifying inequivalent, if there exist, bi-Hamiltonian pairs, in which one of the two is the structure you're studying. Now, in the scalar case, meaning for a system of differential difference equation with just one dependent variable, the classification of the local Hamiltonian structure was done some years ago up to the order -5.5 by De Sole, Valeri, and Wakimoto. And this is, well, a very explicit computation. In fact, I would not even say that there is a classification. I would say that there is a list of all the existing local Hamiltonian operators up to order -5.5. Their proof goes in several steps. First of all, they show very easily that the general form of a scalar skew adjoint operator must be like of this form for sum of k from 1 to n. Then they prove by the Jacobi identity for a multiplicative Poisson vertex algebra that each of these functions fk cannot have arbitrary dependence on the sides, but start from u and stop at fk, where fk is the corresponding order. And finally, there is the hard part of the computation, showing all the possible form of this f that give Hamiltonian structure. There are two families of Hamiltonian structure, of Hamiltonian operators, general and complementary. Complementary started to be difficult to explain, so I just copied and pasted from their paper. While general type is quite easy, you see that depends on this function g. And then they explored some exceptional cases, namely elements of this linear combination of elements of this family that are still Hamiltonian, or if you like, that are bi-Hamiltonian. And they did it up to the -5.5 order. It's not, I think, so deeply interesting. However, what we wanted to do with Valeri is try to extend the result to multi-component case, because the example I gave you, K-Volterra, is a very simple and very fundamental example of integrable differential difference equation, but at the same time, in the two-component case, there is a much richer landscape, because you have, well, the Toda lattice, which is as important as Volterra, plus many other kinds of system. And The problem is their computational approach will not work for non-scalar operators. So we went from steps, and we decided to focus on somehow natural but very simple case, -1, 1 type. In this case, well, the skew adjoint operator must have this form, and imposing the Poisson property on this multi-component case is still really, in general, very, very complicated. Now, if the matrix multiplying the shifts is non-degenerate, then you can prove that the dependence on each element A and B is similar to the one of the scalar case. Unfortunately, if A is degenerate, and this is the case already for Toda lattice, you don't have this necessary condition. And that means that a direct computational approach is rather hopeless in general. So this is how it looks like if you admit that that A and B depends only on the same number of shifts of the non-degenerate case. You see that the so-called ultralocal part, the one without shift, is just a Poisson bivector, because this is the Schouten torsion of a bivector and n-dimensional manifold. This is much more involved, and it is surprising in a sense that many years ago the non-degenerate case was solved. It was solved by Dubrovin, and then and the proof of this result is actually not it's not there in the paper where this result appears, and the proof appeared only many years later in the PhD thesis of one of the Dubrovin student. And the idea is that when the first matrix A is non-degenerate, then all the Hamiltonian operator, or the Poisson bivector of order 1 minus 1, are in one-to-one correspondence with so-called admissible Poisson-Lie groups, meaning with Poisson-Lie groups with some extra requirements. So as a Poisson-Lie group, I mean, this is definitely not the audience to which I should remind what they mean, but we consider a Lie bialgebra and integrate it. That gives a Poisson-Lie group. Integrate means and the Poisson-Lie group is a Poisson manifold where the Poisson bivector, the derivative of the Poisson bivector and the identity are the structure constant of the coalgebra, and it is vanishing, and this gives you the Poisson structure, a Poisson structure on the manifold. And by admissible, Dubrovin means that there exists a solution of classical Bach's equation of classical CB. Why so CB? Classical Young-Baxter equation with such that if you deform your coalgebra, you get still a coalgebra, and a Lie algebra homomorphism that is in our matrix, such that you can also have a Lie algebra homomorphism between your deformed coalgebra and the original algebra. I mean, these are strange data that you need, but what it is proved is that if you have this bunch of elements, you can take a basis of left and a basis of right invariant vector field on your Poisson-Lie group, and use them to define the matrix A and the matrix B. Why? You do the computation and it works. A deeper understanding of that surely is not there in the PhD thesis, where these things are detailed. And if it was in Dubrovin's mind, as it probably was, he never wrote it anywhere. So, but this really gives you all the possible Hamiltonian operator of that form, with the problem, and that's okay. Before going to the problem, let's see this in practice. If you take the case of two components like Toda, then in fact you have essentially only two solely groups on two dimensions because you need to take a Lie group with two generators, either the abelian or the non-abelian one. And if you take the construction for the non-abelian group, you have some freedom in defining your R matrix, in defining your coalgebra. And for a suitable choice of these three parameters, you land in the second Hamiltonian structure of Toda, because Toda is a 3-Hamiltonian operator, but in particular, the first and second structures are of order -1, 1. So this lands in one of the two. On the other hand, if you take the abelian group as it is, quite easy to imagine, you only get constant Hamiltonian operator, constant with non-degenerate A Hamiltonian operator. But this is a bit of a problem, and this result apparently was forgotten for quite a simple reason, and the reason is this theorem only characterizes operators that are non-degenerate in the leading term, but most of the relevant integrable system, integrable bi-Hamiltonian system of differential difference type are actually known to be bi-Hamiltonian with a Hamiltonian operator which is degenerate. So this does not say anything about it. It's almost lucky that the second Hamiltonian structure of Toda is non-degenerate in the leading order, so you can find it with this construction. Because, for example, the very, very simple first Hamiltonian structure of the Toda equation does not belong to this classification. And what we did with Valeri is indeed to study what happens in the two-component case where A is degenerate. And these up to change of variables, by change of variables I really mean diffeomorphism of a target manifold, so point transformation for people in integrable system. You have that all the possible forms of Hamiltonian operator are of these three families. So essentially either constant. That, of course, doesn't mean that in general you will have constant operators, because now if you take a constant operator and change variables, you get non-constant operators. But this is like the normal form. And then you have another two forms that are essentially non-constant, even up to change of coordinates. Luckily enough, the first Hamiltonian structure of Toda is of the first type. I mean, normally we write it in the non-constant form, but it belongs to this family. Notice that, well, as I said before, since this matrix A is degenerate, there might be a dependency on further sides that you don't catch with the condition that I wrote before. So, for example, this is absolutely Hamiltonian, even if it has arbitrary dependence on the variable v there. And as I said, first Hamiltonian structure of Toda that normally is written in this form is one of the simplest one. It has constant normal form. Now, second step, and I have not long, so I will not enter into details, unfortunately. I really like this proof, but I never have time to go through it. Sorry. Is how we can compute the Poisson cohomology of these operators. And in particular, I would say of the constant one, which is the one that is the most relevant. The idea is taking to the difference word what is essentially done by Siciliu and Eugene Zhang for PDEs, for the Hamiltonian structure of PDEs. The main technical point is that on one auxiliary complex on densities rather than on multivector fields, you have that the Poisson operator is really looks like the RAM differential operator, so you can use the rank homology of this auxiliary complex to find the Poisson cohomology of the full complex. And for our Toda, essentially, which is, oh sorry, this is the old one. So for our Volterra, this was the final result of the Poisson cohomology. Notice in particular that the second cohomology was trivial, so the discourse about not equivalent by Hamiltonian pairs is, well, no, they are all equivalent. And for the two-component case, this is Toda and this is the result. Notice here that the second cohomology is non-trivial. So here there is space for not equivalent bi-Hamiltonian pairs under Mura transformation. This is a bit interesting, and I would like probably finish on this remark, because despite going through the pain of finding compatible Hamiltonian operators up to the fifth order in the Sole, Valeri, and Wakimoto, all the bi-Hamiltonian pairs that are different that they found had this tiny problem that if you use the bi-Hamiltonian pair to use by-Lenard-Magritte scheme to derive the Hamiltonian hierarchy and the integrable hierarchy, all this hierarchy that you could obtain were just Volterra after some Mura transformation. And okay, they make it as a remark in their paper, but I think that this can be interpreted in the light of our result with Wang in 2020 because of the triviality of the second cohomology group. While in our two-component case, we have some hope of finding new bi-Hamiltonian operator. In the paper, we propose an algorithm for looking for new bi-Hamiltonian pairs. But what is really happening is that going through the list that has been published in some review paper of two-component integrable systems, admitting the operator equivalent under transformation to our first Toda, all those that have been published are in fact in trivial. I mean, are all the second Hamiltonian structures are trivial cocycle and trivial boundaries of the first one. So the list that we have in this review paper is all of equivalent bi-vector pairs. And that's all because I ran out of time. So even if I wanted to speak more.
Well, thank you very much. We have time for one or two quick questions.
So, for example, for the total lattice, and do you consider the asymptotic condition for this variable, for this u or v?
Oh no! If you like this kind of formal notion of local functional, correspond to either an asymptotically vanishing solution on an infinite lattice or a periodic space. Both of these, I would say, analytical properties of the solution correspond to this formal integral.
Do you expect the generalization of your approach to the non-commutative case?
Okay, from the point of view of the Hamiltonian operators, yes, and we already did it in two papers with Jinping Wang about recursion Hamiltonian operators for a differential-difference equation. We redid essentially this supergeometric construction and use it to study and identify Hamiltonian and bi-Hamiltonian operators for non-abelian differential-difference equation. The part of the Poisson cohomology, we really didn't do anything yet because I don't know enough different non-commutative geometry to understand what would be a nice non-commutative cohomology. I mean, what would that mean? But no, that works in the same way. Yes, absolutely. Yes.
Okay, more questions?
Okay, sorry. There is a small difference. The local functional on which you construct everything is not just this quotient I showed. You must also have a quotient with respect to a super commutator of your elements or a super trace. No, yeah, non-commutative. They are non-commutative as fields, but the observables are, if you like, they are trace of integrals. So the local functionals are also quotiented out by supercommutator, because they mimic these trays of the integral.
Hey, thanks for the talk. I want to ask about like, have you heard of like these n-plectic higher symplectic structures? That was studied by John Baez.
I think I should, because I have the impression that someone already told me about them, but I don't really know them.
Because it seems that like the shifted cotangent complexes, it just allows you to get all of that, like get all like the entire tower of these higher symplectic
It is surely
structures.
related again. This kind of things that I remember studying long ago. This of this L infinity structure.
Exactly.
Yeah, absolutely.
Thanks.
Yeah. Thank you.
All right, let's thank Matteo again.